Hello, everyone. Our next section of the course is to do calculus with both trigonometry and then with exponential and logarithmic functions. Okay, so for each of these parts, I'm going to do a little review. So this is a brief trigonometry review of some of the things I need you to remember from advanced functions, okay, in order to successfully complete this section. Okay, so the first thing is just remembering what radian measure means. Okay, so the radian measure of an angle is the ratio of the arc length to the radius, right? So we write that theta equals A over R, right? It's just this divided by that, okay? More importantly here will be to be able to convert degrees into radians. Like if you have a situation that involves degrees, you're going to have to convert it to radians because in terms of calculus, the trig functions have to be in radians pretty much for it to work, okay? So just as a quick review, if you want to convert, the conversion factor that you probably used is you note that a half circle, right, that's 180 degrees, okay, and that's equal to pi radians, right? A full circle would be 2 pi, so half the circle is just pi. So it means that 1 radian is equal to pi divided by 180. Okay. So if I want to convert from degrees to radians, right, then I'm going to multiply this by pi over 180. Okay, that gives me 60 pi over 180, and when I reduce the fraction, I get pi over 3. Okay, so just again, second angle, same idea. I multiply by a conversion factor, pi over 180. Okay, that gives me 72 over 180. Okay, and then clearing up the fraction. Does that work out nicely? Yep. Okay, so that gives me 5. Wait a minute, that is 2 pi over 5. Okay, and a lot of calculators, I mean, if you have a nice display calculator, it might actually reduce those for you automatically. Like on the calculator I'm using here at home, if I do 72 pi divided by 180 and press equals, it automatically gives me 2 pi over 5 right on my calculator. Okay, so if you have that option, that's handy. Okay, secondly, we're going to talk about is the graphs, right? We know that as a sine or cosine function that we can model it something like this, okay, where A is the amplitude, right? So this is my amplitude. Okay, 2 pi divided by b is the period. So that's my horizontal stretch affects the period of the function. Okay, and the last two things are my phase shift and my vertical translation, right? So this part controls up and down. This part controls left and right. Right? Notice the presence of these other brackets in here. A common, I don't want to say trick, but something we would have done to you in advanced functions would be say if your function is sine of 2x minus 4, that you have to recognize that that's really sine of 2 times x minus 2, right? You have to factor it, and that means that your phase shift is 2 to the right, it's not 4 to the right. Okay. So a quick example of that is here's a graph, okay, and we're going to determine the equation of the graph. Okay, so first thing, we'll note the amplitude. Okay, my amplitude is 2. Okay, so that means my a value in the equation is going to have to be 2. Okay, next thing is the period of the function. So on my graph, I have a complete cycle of the graph from 0 to 2. Okay, the period is 2. Okay, we said that that expression 2 pi over b is equal to the period of the function. So 2 pi over b is equal to 2, and I have to solve it for b. Okay, so the 2 comes down, the b goes up, so pi is equal to b. So in my equation, I'm going to see a pi present there. Okay, for vertical shift, we'll jump down to that for a second. Okay, it doesn't go anywhere left or right. Okay, so there's no vertical shift, so that c value in that equation would be 0. Okay, for horizontal shift, it depends how I want to model this function. So actually, I think I'll end up doing like 3 equations here. Okay, let's start with if we wanted it to be sine. Okay, sine starts at the axis and goes up. So that would be a phase shift of 1. So putting that all together, one equation I could write for this would be y equals, okay, my amplitude was 2. I'm going to use sine. Okay, my b value is pi. Okay, I have a phase shift of 1 to the right, so that's x minus 1, and there's no vertical shift. Okay, so this is one way I could write the function. Okay, if I wanted to use cosine, okay, then it starts at a peak, so I would have to check here. That's at 1.5. Okay, so I could write this function as y equals 2 cosine pi x minus 1.5 or 3 over 2. Okay, and then again, there's no vertical shift. Okay, last but not least, a third way I could write this function is to say, well, it's actually sine but flipped over, right? Sine normally starts at 0 and goes up. This starts at 0 and goes down. So I could just make my amplitude negative to reflect the fact it's flipped over. So a third way I could write this function is that y equals negative 2 sine of pi x. And that would be it. Okay, there'd be no horizontal, or sorry, no phase shift, no vertical shift at all. Okay, so yeah, there's lots of ways to represent the trig functions. Again, in terms of phase shift, we usually pick the shorter one. So actually backing up for cosine, I really should have used this one going the other way, because that's a shorter phase shift. So instead of doing minus 3 over 2, I really should have done plus a half, because that's the shorter phase shift, going a half to the left. Okay. Okay, third thing we're going to talk about is the unit circle and special triangles. Okay, I guess if you don't have one in your binder, say from advanced functions from before, they're pretty easy to find online. Okay, either of these two things. Just some of the ones that you're hopefully familiar with by now are for 30, 60, actually, this should be 30, 45, and 90, and 60. Okay, so for example, first, the angle, right, 30 degrees is pi over 6. Okay, but knowing that sine of pi over 6 is equal to 1/2. Okay, cosine of pi over 6 is equal to root 3 over 2. Okay, to get tan of the same thing, we'd just be doing sine over cos. So you'd have 1 over 2 over root 3 over 2, kind of the 2's would cancel, and the tan would be 1 over root 3. Okay, so for these special numbers, right, knowing what the exact values are. Okay, for 45, right, that's pi over 4. Okay, both sine and cosine are 1 over root 2. Okay, and for tan, it's 1 pi over 4. Okay, and for 60 degrees, which is pi over 3. Okay, so sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. Okay, and tan of pi over 3 is equal to the square root of 3. Okay. You might also want to remember things for 90, right, and 0, like some of the basic ones. You know, sine of 90 is 1, cos of 90 is 0, tan of 90 is undefined. Okay, some of those. But these are the ones that will come up often in terms of exact values. Okay, so for a quick example of that, determine the exact value of sine of pi over 6 plus secant of pi over 4. Okay, so to help us out here, this is sine of pi over 6 plus, we remember that secant is related to cosine, so that is 1 over cosine of pi over 4. Okay, sine of pi over 6, that's 1/2. Okay, cosine of pi over 4 is 1 over root 2. Okay. So to flip this fraction around, just again on the side, that means I have 1 divided by 1 over root 2, which is the same as 1 times root 2 over 1. So it's the same as root 2. So I have a half plus root 2. Okay, and just for the practice, we'll get a common denominator here. So I have a half plus, I would have 2 root 2 over 2 for a common denominator. So this is 1 plus 2 root 2 over 2. Okay, last thing we're going to briefly talk about is your favorite part of the trig course, trig identities. Okay. And if you had me for advanced functions, I probably mentioned one of the reasons we learn these is basically to simplify derivatives when we get to this point, because that's part of one of the tools that they can be used as. So in the very back of your textbook, okay, so if you open up the back cover, there is a section on trig, okay, and there's a section on identities. Like I'm looking at it right now, and it says fundamental identities, reciprocal, quotient, okay, a whole bunch of different things there. All right. So yeah, it's using those to simplify expressions. So we're going to prove that sine squared times secant squared is equal to secant squared minus sine squared minus cos squared. Okay. So both sides are a little bit messy. I'm going to start with the left-hand side here. So one of the things you probably learned, okay, is it's helpful to put things in terms of just sine and cos. So this becomes sine squared theta times, okay, secant is 1 over cos. So it's 1 over cos squared. So left-hand side. Okay, so this becomes sine squared theta over cos squared theta. And that simplifies to tan squared theta. Okay, that's pretty simple. So it would be helpful if I could try to turn this into tan squared theta as well. Okay. So again, there's multiple ways to go through this. What I'm going to do is that sine squared cos squared looks like it would be helpful. So if I common factor out the negative, it becomes sine squared plus cos squared. Okay, and that becomes secant squared minus 1. So where do I go from here? Well, if you go to those identities in the back of the textbook, okay, under fundamental identities, it says tan squared plus 1 is equal to secant squared. So I'm just going to jot that down underneath here for a second. This is the identity I'm going to use, equals secant squared plus 1. Okay, whoop, back that up. I got ahead of myself there. It's tan squared plus 1. Oh, I did it again. Tan squared plus 1 equals secant squared. Okay, that's the identity I saw in the book. It's related to sine squared plus cos squared is 1. So if I just move the 1 across, that becomes secant squared minus 1. So that means this expression right here is equal to tan squared. Okay, and so that's proven. So you have a variety of ways to sign this off. Okay, one way is you can draw a little box. Okay, another way is you can write QED. Okay, another way is you can write left-hand side equals right-hand side. Okay, you don't need to do all three. One of these will do when you're signing off a proof. Years and years ago, I had a student who every time they did an identity, they wrote all three and then they signed off their own name. They wrote like Jeff Rules or something like that because he was just so excited he'd gotten through one. Okay, but again, key skill, being able to make these little manipulations, that'll be helpful in terms of simplifying derivatives as we go through. Okay, thanks for watching. And here is some practice work if you need to do some review from Trig.